Good morning or afternoon, depending on where you're from. Thank you for joining us here for another wonderful webinar on our automation webinar series. My name is Zachary Stank. I am the product manager for the Control, Safety, and I/O products here at Phoenix Contact USA. I'm excited that you've taken some time out of your day to join us live to go over the distributed I/O history and latest technology. Joining us today, we have Jason Haldeman, who's our Senior Product Marketing Specialist for I/O products. Jason has been with Phoenix Contact for a number of years and has a ton of experience with our I/O line, and is also very experienced in I/O history as well. So I know we're going to have a good presentation today. A few reminders before we get started. If you recall that we are on a 20-second delay between us producing the video and you receiving it. So if you have any questions and you put them in the live Q&A and we don't get to it, it's not because we don't want to answer it. It's because we probably already passed the opportunity to answer that question. So just keep that in mind when you're asking questions. The other thing is, I'm sure you've already registered for this on phoenixcontact.com/US-webinars. I will be putting that link again in the Q&A here for everybody to see. You can go visit and sign up for other webinars that you may be interested in. And also we have changed the website to now allow you to click any previous webinar and you can view that right from that page. So some good updates there. I will also say that here in central Pennsylvania, we have some inclement weather coming our way. We're hoping that everything is fine and that there will be no power outages, but however, if for some reason, either of us do go offline and we cannot continue the webinar, we will reschedule it and start fresh on that one. But I think we're going to be in the clear here. So without further ado, Jason, thank you very much for joining us today, and the stage is yours.
All right, thank you, Zach. Again, my name is Jason Haldeman. What I want to do here today is just to kind of give a general introduction into the world of I/O. I've been with Phoenix 24 years, so I hate to say I lived a lot of this. Not some of the initial beginning stuff, but some of the conversion from the serial networks over. I've kind of been involved and seen and supported these different things. So kind of what I wanted to do is just go through what is I/O when I say that, and how and what issues have we gone through over the years of trying to get these I/O signals back to our PLC and back through our system through parallel wiring, distributed I/O, serial Ethernet networks, and all those things. And then at the end, just for a few minutes to kind of touch on, wow, the collection of the I/O has changed. The I/O modules themselves have changed too, because they had to adapt to all the new things going on inside of the market, and the new things inside of the market, and how this data needed to be collected in a small footprint and everything else. So to kind of start it off, when I say the word I/O, what the heck is I/O? I/O is information. So any industrial application needs information, and information comes from sensors. Sensors are usually broken into one of these four categories. Obviously, digital. A digital sensor is a simple true or false, on or off. It is a value that comes back. It could be from a proximity sensor that senses a metal or the presence of an object in front of it. It could be a physical limit switch, something that when you push the switch, you close a physical contact. And what happens on these sensors is they send a voltage. So when the sensor is true, a 24-volt signal is present. That signal is then read as an I/O point, and then we need to get that information back to our controller to create some type of logic for behind that. Originally, a lot of these were at 120 volts back in the beginning when we were doing more of a true relay logic cabinets. But today we're kind of standardizing on the 24 volt for these, but we still run into the 120 volt area. Next is the analogs. Analog signals are basically if digital's not enough. I have a tank. The tank is either, I could put a float valve on that tank, and then when the tank is, if the tank is not full, I get a value of 0. When the tank gets to the full point, the float switch triggers. I get a digital input. I know the tank is full. In some applications, that's perfectly fine. All I need is an empty or full. But there's certain applications I need to know a little bit more. I'd rather know how close to full am I. And that's kind of where analog comes into range, because now what you can do is you can take that same float sensor, replace that hard limit switch with a analog value or an analog representation of a percentage. Is it empty? Is it full? Like a 0 to 100% type thing. And the way that we were able to represent this, because with 24 volts, it's either on or off. So what they're doing is they're taking either a voltage or a current signal and using that as our 0 to 100% value. So if the tank is empty, the float's all the way at the bottom, we're going to get a 0 volts. If it's all the way at the top, we're going to get 100 or 10 volts. If it's somewhere in the middle, or if it's right in the middle, we'll get 5 volts. That gives us a scalable range to allow us to be a little bit more granular on the information that we get. So with these type of inputs and these type of I/O devices, we need to have an I/O module that can actually basically function like a multimeter. It's able to read the voltage and tell us what voltage it's coming from the sensor. And European, it's traditional to use a 0 to 10 volt signal. In the US, we use a 4 to 20 milliamp signal. Basically, we're supplying a constant voltage. We vary the current with it. I think it's a little more a little better when it comes to noisy environments versus voltage ones, but either one really functions the same. You're either varying a voltage or current to generate a signal. And then last, temperature. Temperature is always very important. Yeah, you're measuring the temperature of a liquid, you're measuring the temperature of a machine or the environment. So temperature becomes a very important part of applications, and knowing what temperature your environment's in is a key portion of it. And this is usually done through either RTD or UTH modules. Both of these, the same concept as analog, other than it's a lot smaller of voltages usually involved. So a UTH, basically the 50,000 foot explanation of UTH is basically taking two dissimilar wire types, twisting them together. These two wire types create a chemical reaction under temperature, and that chemical reaction generates a voltage. So UTH basically is a very, very small voltage that changes over temperature, and then we can use that to figure out what temperature the environment actually is. RTD is the same idea, other than it's a variable resistance. Resistance goes up or down depending on temperature, and our input module that we have to use is going to be a device that basically measures resistance. And then, of course, the other. As time goes on, as systems get more complicated, we keep having to create custom I/O devices to be able to collect different types of signals from counters and encoders, things that have bit streams or other variations of collecting data to be able to get it through the system. So that's kind of where we put the other. But some of the most common are encoders when you're measuring motor and motor direction. Counters, you have high-speed counting that you need to kind of do locally because you can't go through a standard I/O card, can't count something fast enough. And power measurement, that's a power monitoring, power measurement. This is another key area with everything going renewable and energy monitoring systems like that. So you do some of those basic functions inside of it and then pass the raw data in through some type of serial or some type of data communications connection to the sensors. But it's all based and part of the I/O module itself. So when it comes to I/O, there's a lot of different things we need to see, or a lot of different types of signals we need to read, because we got to get this information back to a PLC so the PLC can make a decision, decide what to do with it, and then in turn send that information back out through output modules, these same modules in reverse, pushing signals out so that we can control the function of the PLC. So how do we do this?
Hey, Jason, do you have time for a quick question already?
Sure.
Okay, there's a question about the temperature one specifically.
Okay.
The question is RTD versus UTH. Is there like an industry standard, or is it basically application specific?
It's hit or miss. RTD, again, this is where that comes into the RTD is heavier in Europe. UTH is heavier in the US. RTD is a little bit lower on cost perspective. So I'm seeing an influx in RTD into the US market just for the cost savings behind it. But UTH is more common, and UTH is broken down into all these different variations. UTH, I could spend days going over different thermocouple types, thermocouple variations in metal, and the various metal types that come together. But in the end, it comes down. In the end, it comes down to the sensor you need and what type of connection it gives you. It's really, but those are the bases. So We have signals. Now we need to get these signals to our PLC. How are we going to do that? Well, in the past and still today, because it's still commonly used, you basically have your analog signals out in the field. You want to get those signals to the PLC. What you do is you place I/O cards. These are these little gray slots to the right of the PLC, and these I/O cards are our digital and analog I/O card slots, and then we just physically wire them back to the PLC. It's easy. It's simple. This works great today, small machines, things like that. But what's happening over time is that machines are getting more and more complex. We need to get more and more I/O signals. So what do? We just keep adding more and more I/O cards into the PLC. The problem that we run into is there comes a point, there comes a breaking point, a point where I have so many wires that I need to bring back into a single location. It becomes difficult physically to get all these wires into the cabinet. How many holes can I drill on the side of the cabinet to shove wires through? How many conduits can I run in there? What distance can I run? These machines get bigger. As cables get longer, they have more of a voltage drop. Oh, well, to counter that voltage drop, I'll just make the wire gauges heavier. Well, as I make the wire gauges heavier, what happens again? Now the cable costs start going through the roof. Copper's not cheap. So everything that we're doing inside of the machine is adding more and more cost because we're trying to simplify the design and just have everything wired back to a single location, aka parallel wiring. This works great for a lot of applications today, especially if you have a small widget machine that supports a little function and it may not require any type of distributed to get to all the sensor points. But machines keep getting more complicated and these cable lengths become an issue. So basically, there needed to be a solution. We needed to, or PLC manufacturers needed to figure out a way around this, another solution, another direction to go. And they really sat back and they started looking at, well, what can we do? What technologies are out there? What is available that I can look at or use to get this information back to the PLC and reduce some of this cabling? Well, at this time, you'll notice on the PLC, there's a serial port. This serial port has always been there, and that serial port has always been used so that I can download my programs to the PLC. So they've used serial. They realized that this was a great communications to go from my computer to my PLC to download data bit streams to basically the program into the PLC to download it into the memory, switch it to the run, the PLC runs and does its function. So they already knew that they could rely on the serial communications for the protocol, but at this time they were looking at all the technologies that were available. Well, we have serial, RS-232, 485, 422. These have all been around since the 60s. They've been readily used for communications between devices, between computers, printers, things like that. It was pretty well established. But at the same time that they were trying to make this decision, they also had to look at the possibility of Ethernet. Now, at this time, Ethernet wasn't Ethernet yet. Ethernet was a bunch of competing technologies trying to figure out who was going to win, and what technology was going to run. So you didn't have just Ethernet. You had token ring. You had FTDI. These were other variations of pretty much the same concept, just like you have 232 to 485, but these were competing technologies, all competing for the same space to give us a communications mainly focused on the office network. So at this time, Ethernet was there, but it wasn't quite ready for prime time yet. It was still early in its infancies. It was still limited in its functionality, and it lacked some basic controls that we needed to be used as an I/O network. We'll hit some of those up here in the thing. So basically, all the PLC manufacturers went out. They all started looking at the serial communications as options. Step one is they just looked at, well, I'll just network my PLCs on a serial network and they can talk to each other. This was not cost effective. The processors are expensive. So they're looking at, well, we got to simplify this. We got to get the I/O cards and move them to the field. Not the processor, not the brain of the PLC, because that's the expensive chunk, but just the I/O cards. So they're looking at, okay, well, let's look at these individual serial technologies and figure out which one will work for us. Now, they're all great. They all work. They all have their advantages and disadvantages over depending on environment. You got 232, which is a point-to-point network. You have RS-485, which is a point-to-multipoint network. Again, just communications and just the way. And then 422 is another point-to-point network style. These are all just communications concepts or physical mediums that were used. The data on top of them was completely proprietary to whatever, or the data that was run on top of them was all dependent on the application. And the application is the software or the computer or the PLC or the communications between the PLC and the I/O device. So as they were all looking at serial, all the PLC manufacturers started jumping on different protocols and different bandwidths, trying to decide which is better and which is better than the competitors. This was the birth of what we call the bus wars. This is where every PLC manufacturer came out with their own concept that they all ran around talking about. Mine's better than yours. I can do more devices. I can go better distances. I can go faster. You're too slow. All these different comparisons between each other really surfaced. This is part of the area where I jumped into Phoenix, and this is where I've lived at the beginning, where we would try and have the conversation on why my network was better than your network and you should use my components versus theirs. But the main pushers behind it were, of course, the main PLC manufacturers. In the top left, we got DeviceNet. This was the Rockwell network of choice. So the Rockwell created the ODVA, which is their organization behind it. They created a serial network based off of RS-485. Oh, lost my mouse. Based off of RS-485 that allowed them to network devices together using a serial cable, a 2-wire system. They could do up to 64 devices. That's a lot of devices, because if you think of like an I/O card, the PLC on the last page, what could you put in there? Like six I/O cards. So instead of doing 6 I/O cards, I could put a DeviceNet interface in that PLC, and I could go out and talk to 64 I/O devices. And I could choose between these different baud rates for what type of speed that I wanted to collect the data if I needed it faster or not as fast. Speed relates to distance, so as you speed it up, you're then reduced to the cable length that you can have inside of the system. So they were all kind of relevant with each other. Profibus, same type I/O, or same type concept. This was with the Siemens company, with the Siemens PLC. They went with the Profibus concept, still based on RS-485, so they both jumped on the same bandwagon there. But they set up their devices a little differently. They set up the way their devices are addressed. They set up the speeds a little bit differently. And like both of them, they set up the way the data is formatted on the top end differently, making them completely non-compatible with each other. Even though they still use the 485 concept, in the end, they looked like completely different networks. You wouldn't recognize them both as a 485 communications protocol. And they did support some different baud rates from 9.6K all the way up to 12 meg. Some serious speed that they could push through a serial cable. To be 100% honest, I saw very few 12 meg systems actually working because I think they were pushing their speeds a little too much. They created a lot of noise and a lot of issues behind them. And then Schneider invented the Modbus RTU protocol. This was the protocol. This was a very popular protocol for a while, because this was also while it was the Schneider protocol, it was also the homespun protocol, the protocol people would use when they're trying to use the serial ports on their computers to do their own homegrown programming. This was based off of both RS-232 or 485, so you had the choice of the different protocols you wanted to use in the connection depending on the devices and the nodes and the baud rates. But in the end, it's all the same thing. It's all about collecting data. Oh, excuse me, and getting that data back to the PLC. And then, of course, Phoenix Contact didn't want to be left behind. We had some of our own controllers at the time, mostly PC-based control, but we understood that, you know what, we had an I/O network based on RS-422. We were a little different than everybody else. And the reason we went with 422 is because it gave us an advantage of distance. We saw a void in these networks where, you know what, we want to cover some further ground. We want to be able to put more distance in between the I/O devices. So we created a network called Interbus, and we created cards that sat in the Rockwell, the Siemens, and the Schneider PLCs so that we could use our interbus network tied to their PLCs. We kind of opened them up to a different protocol and kind of took advantage of that. And with that, we came out with our own form factor of I/O. I dug through some really, really old pictures, and I dug out a few products that you could see. That's archaic looking technology, but this was the cool thing at the time. This was amazing that we could take and create these large I/O devices and be able to distribute I/O signals either from a computer out to the field, from a PLC out to a field, and through long daisy-chained I/O networks. So Phoenix Contact jumped in the game. This is kind of where I came out. My first job was to support or do phone support and technical support for this type of product. So in the end, what did this do for us? So during the bus wars, everybody's PLC, everybody had their own concept. The first thing they had to do is they had to free up some slot on their PLC or free up some backplane area on their PLC. So first thing we're going to do is we're going to cut the wires off. All right, their wires are off. Now we're going to replace one of these I/O cards or two of these I/O cards, depending on the size of the master, with the new serial communications interface. So it's an I/O card, but instead of it having wires to go to I/O signals, it's going to have a connector, a serial connector to go out to the network. Then we're going to create a new I/O module that sits directly out in the field, close to the sensor. We're still going to parallel wire all of our I/O signals from the sensor to our new I/O card. But now, instead of those parallel wires running all the way back to the PLC, we're now going to take those bits of data, we're going to bring them in via parallel wiring, we're going to line them up into a serial bit stream, and we're going to push them through this cable all the way back up to the PLC. In the end, technically, the PLC is still doing its same function. It's still looking at the raw data from each of these bits and words, depending on whether it's digital or analog modules, and it's still performing the exact same function. We just pulled out an I/O card and replaced it with a new card that has a little bit of smarts in it that can actually handle the communications to these end devices. This gave an advantage for cabling. We reduced copper cost. Yes, we added cost for I/O modules. But in the end, copper is expensive, and we reduced a lot of copper costs that it became an advantage to going with a little bit more complicated serial and bus network to collect this data and bring it back to the system. It also cleaned up system design. It made it easier to work with and easier to troubleshoot because these I/O devices can now contain some base diagnostics and able to diagnose what's going on at their individual stations so that we're able to bring this diagnostics back into the system to provide a mechanism for the PLC to more easily diagnose problems at the individual I/O modules in the system. And then last is because this is a closed network, this was a deterministic network. This is the reason Serial won for the initial concept of an I/O network, is because Serial is a closed communications protocol that requires a master. It requires that somebody is in control of the communications, and that is this card. This card is configured to handle communications to each of the individual devices on there. So basically, the controller goes, give me your data to station 1. This is broadcast across the entire network. Whoever is station 1 is going to just sit and listen and go, oop, I'm station 1. I'm going to respond with my data. Then it's going to go, I want data from station 2, data from station 3, station 4, station 5, and a sequence is generated. This sequence of commands for pulling data between I/O devices allowed them to create a network that was deterministic. This was key because I need to, as a programmer, know that I'm getting my data in a timely manner every single time because my program counts on it. When I see a sensor turn on, I turn something off. If I turn a sensor on, a sensor turns on, and it takes me 10 milliseconds to get that data, 100 milliseconds to process that data, another 10 milliseconds to turn the output, I know I have a 120 millisecond cycle in that. Now, if it takes me 10 milliseconds every single time, I can make that as a part of my program. But if that varies, if it takes me 10 milliseconds today, tomorrow it takes me 60 milliseconds, I could actually throw the sync of my program out. So it was important for these networks to be deterministic. That was the key word. And that was the key fighting phrase between DeviceNet and Profibus and Interbus. My network was more deterministic than your network. I could turn my I/O on faster than you can turn your I/O on. And this was really a key focus behind there. And this was a key thing that Ethernet was missing, specifically at the beginning when it was first really being developed and hitting the market. Some of the disadvantages with any network like this: you now need to have software, you need to have hardware, that you need to have tools to program it. You have to set up addressing on individual devices. This could be software-based addressing, it could be hardware-based addressing. You might have rotary switches you have to set this one to ID1, ID2, ID3, things like that. You also needed to have a configuration in the PLC. In this card, some tool needed to be used to tell this device how many of these are out here and how much data those have. So that they did add a complexity with the initial configuration of the system. And then finally, because all of these networks are built on slightly different protocols, they're built on 485, 422, RS-232, that made them completely non-compatible with each other. So if I have a PLC and a system running DeviceNet, and then I put it next to a system running Profibus, and I decided I want to share data between these networks, I can't. They're not the same protocol. There was no way of getting the data between without purchasing a hardware piece called a gateway. That gateway then would allow me to do the communications between the two, because it would be a hardware piece. So this was a little expensive. So while serial was great in its determinism, it saved us space in our parallel wiring. It was still very limited and a very closed system. And at this point in time, once people saw networking, they realized this is great, but I want more flexibility. And flexibility is not what serial networks had. So while all of this was going on, another couple of years, 10 years or so had passed. The bus wars, everybody was fighting it out. DeviceNet was kind of winning in the US. Profibus was winning in Europe. Modbus was floating there in the middle, number two slot between the two. And even Phoenix Contact in Europe was right there around the number two, the jumping between the 1 and 2 spot with the Profibus side. We were doing very well. And we did have a good bit of success here in the US. But while we were all doing this, another thing changed. This Ethernet port showed up on the PLC. This Ethernet showed up on the PLC because Ethernet won. The token ring, the FDDI, they fell off. They weren't really the winner of who was going to be the next Ethernet. Ethernet, we call it Ethernet, so Ethernet was obviously the winner. And because their technology won the concept, we realized, well, all right, so we're using our serial networks because they're very deterministic. Ethernet has a really cool open flexibility that we want to take advantage of, because me as a programmer, I'm lazy. I don't want to go out there with a serial cable hooked to my computer and plug it into the PLC to program it, because back then I wasn't walking around with a laptop. I was walking around with a big old desktop computer. So I had to drag everything out there, drop it down, and then plug the serial port of my computer into the serial port of this and download my programs. But if I used Ethernet, Ethernet allowed me to network my PLCs and get that network cable all the way back to my computer, and I didn't have to leave my desk. So they realized Ethernet, while not as deterministic as the serial networks, was still very valid and it had a purpose on the PLC for this higher end communications, for downloading programs, for monitoring the status of the PLC, and even for HMI purposes, for getting data up into your SCADA systems. So Ethernet was becoming prevalent, but it was still only at the PLC side. So this serial port, while it's still here, was slowly fading away as the preferred Ethernet option was taking over. But Ethernet, oh, excuse me, Ethernet in its original development had some issues. It had not issues, but it was developed for a specific use and a specific way. And it was a specific use that was very different than what we were used to as the serial bus networks, because we kept screaming the determinism. That was the key word that everybody was running around yelling. And Ethernet was not built on a network that was supposed to be deterministic. It was built on a network that was supposed to be open. Open, that anybody can use it and take advantage of it. They just had to have an interface that allowed them to sit on it. So having it open was more important to them because they wanted to have that open flexibility, because they knew that there was going to be more types and different types of devices on the networks. Devices that may never talk to each other, but they just wanted to share the same network and use the same road systems. It's like the highway system. There's all different types of cars. There's not just a road for trucks and a road for cars. We all ride on the same roads. And that was the idea behind Ethernet. It's a single road that everybody can share. But to share it, everybody had to follow a rule. And that rule is there on the bottom right. And it is carrier sense multiple access with collision detection. Everybody's Ethernet port had to follow this rule. And to sit on the network, you had to sit here and listen, and you had to follow these rules, because someone used to use the word the polite cocktail party, or the polite conversation, where everybody's going to sit and intensely listen on the network, and they're going to wait for their turn to talk. So every Ethernet port will sit and listen. If I have data that I want to send from my computer to a printer, my computer's going to sit and listen. It's going to make sure nobody else is talking. Once I've verified nobody else is talking, I'm going to go ahead and take the network channel and start blasting my information out there. When I blast my information, it gets repeated across the entire network. Everybody sees it, but the printer's the only thing that cares about it. The printer's going to absorb the data, it's going to print my piece of paper, and I'm happy and ready to go. But if I'm in the process of printing and somebody else starts listening to the network and their interface also decided a microsecond behind my interface that, oh, the network's clear, I'm going to start transmitting, then a collision will occur on the network. The network will see this, it'll shut down, it'll stop, it'll go, oh no, timeout. The entire network will shut down. Everybody will stop talking. Everybody will go through this mathematical formula of a wait time. So it's a random mathematical formula. So hopefully everybody waits a different period of time before we try again. So it's a very polite system of communications where you wait your turn, but it lacked this deterministic capability that we needed. And also in the initial Ethernet, you could see this cable up here. This is the old Ethernet, the original Ethernet cable. It's the old coaxial network. Even when I started at Phoenix Contact, this was the network that was tied between our computers. We had one cable with these T bayonet connectors that went from computer to computer, and it snaked between from desk to desk, and everybody was tied together on this one cable to get them back into the office network. Oh, excuse me. So just to take a little quicker look at the intro into Ethernet, just to kind of recap what I said. So an Ethernet network, this is an example of a coax network where everybody's tied together, termination resistors, bayonet connections, all just a single cable, no hardware, just a cable. So if I have a computer, it wants to talk, it goes, it listens, it determines the channel's free, it starts transmitting data. Everybody gets the data. The printer's the only one that cares about it. My piece of paper comes out and I'm happy. Now, at the same time I'm trying to print, the person next to me is trying to print also. So we're both sitting there listening to the network, and we both decided at the exact same time, the network was clear. We start transmitting, everybody collides, everything stops, the network shuts down, everybody waits their waiting period, and then the computer's Ethernet port tries again automatically. So I'm not as the person clicking print on my print job, I don't have to click print a second time. My Ethernet port's just sitting there waiting, and it's going to send the data out, which is fine. So it took an extra 2 or 3 milliseconds for my print job to get to the printer. I'm not going to notice the difference there. I just want to make sure that the piece of paper comes out of the printer. Whether my piece of paper came out before the guy sitting next to me comes out, again, I don't care. As long as it gets there, I'm happy. And that's how Ethernet was built, with this in mind. But the idea behind it, it still lacked that determinism capability that we really needed in Ethernet. So over time, Ethernet kept advancing. Serial networks pretty much stayed the same. There was small advances they would do to try and make their networks a little bit better than everybody else, but they were kind of stagnant. But at this time of the bus wars, Ethernet was slowly in the background creeping up. And in the 90s, I believe it's the Xerox Corporation was the first one that came out with the first switch. I don't remember specifically at the top of my head, but the switch was introduced. So the switch caused two things happen when the switch was introduced. First, we moved from the coaxial network to the twisted pair network we're used to seeing today. We have these RJ45 connectors now. So that's the cable we're all used to plugging into our computers and plugging into our any devices we have on our network. And then the switch. The switch took the basic concept of Ethernet and became the traffic cop. The cop that's going to help direct the traffic basically the traffic cop sitting in the middle of the intersection trying to direct traffic, trying to make sure that the traffic keeps flowing as efficiently as possible. So we talked about a slide back how data is transmitted across the entire network. Well, this is a little bit different for the switch because now data comes in a port. That switch actually sits and listens to the data coming in and figures out, all right, well, you came from this address. So I'm going to go to that port and create a table to say, all right, so if anybody else wants to send data to that address, I know only to send it out that port. So it's starting to manage the data flow. As the switches learn, as they sit on the network, they learn where everybody is, what ports everybody's tied to, and they help direct the data flow. So I'm going to try and step back and do that one more time. So data comes in one port, goes out the appropriate port. This took the bandwidth of Ethernet. If you use the analogies of a road, it took Ethernet from a dirt country road and turned it into a multi-lane highway, and created an efficiency on the network that was an amazing leap forward, allowing data to now transmit and flow through the switch in multiple directions without affecting each other. So if I have a computer up here connected to the orange line and a printer hooked up down here, I can send information through this computer to this printer while I'm sending an email from this printer or from this computer to this line at the exact same time without them conflicting with each other, because this will manage and basically make a little invisible line to connect between the two to allow the data to push through without affecting each other. It removed and reduced the collisions in the network dramatically by 80% or more. So by removing these collisions and making the network more efficient, while it is still an open network and it is not a deterministic network, we're making it so efficient through the use of the switch. We created it to be deterministic-ish enough to be used and to be considered as an IO network. And that was really the game changer. Between this and everybody that was using serial networks was completely sick of dealing with the rules behind, I can only have so many devices. I can only go my cables certain distances and certain baud rates. Where with Ethernet, it's kind of more of a plug and play. You plug it together, the switches figure it out, and it just kind of works. You could run copper. You could use fiber if you needed to get bigger distances. To do the conversion between the two was simple. You bought a switch. Like down here, we have a switch that has copper ports, that has fiber ports. We can do both. So we can run copper on one side, fiber on the other. And it also opened up the Ethernet network to support multiple speeds. The original Ethernet was 10 meg when it was launched. Now we're going 10, we're going 100, we're going gig, and it keeps growing from there. And each one of these connections can run at their own independent speed, so that I can take my switch and have gig connections up here. Maybe the green connection is a gig connection because I want to run some high speed data, but I'm only running 100 meg down here because I'm just running some low speed stuff. So you have bandwidth available to you through the switch. Complete game changer. When the switch hit the market, everybody realized, oh crap, this is going to be the next new cool thing. We need to do something about it. So immediately all the PLC manufacturers said, well, I'm jumping on that bandwagon. I'm sick of trying to deal and manage my serial networks because, again, they kept getting bigger and more complicated. And they all took their protocols that they had developed on their serial and simply moved them over and encapsulated them inside of Ethernet or inside of TCP packets, inside of an Ethernet packet. So this allowed DeviceNet to easily transfer over to Ethernet IP, Profibus over to Profinet, and Modbus to Modbus, Modbus RTU to Modbus TCP. They use the same symbol for both. It's kind of a universal thing there. But this allowed them to make this transition over to Ethernet, to realize that, you know what, we need to take advantage of this flexibility. We can give up a tiny bit of determinism for an amazing amount of flexibility, because the flexibility was the next thing everybody needed and wanted, and it was well worth the trade-off. So what happened? Everybody went and adapted their IO cards. So now we have our IO modules. We're going to replace the serial connectors on the IO modules with Ethernet connectors. So now they can talk Ethernet. I'm going to have my Ethernet port on my PLC, or if I want to dedicate, put a secondary port on there. And then I'm going to simply put a switch out there in the network and connect everybody together. Boom. I have an Ethernet network. Ethernet also allows me to be flexible. So here's an example of what we would consider a star network. So I have the PLC connected to the switch, and then everybody connected from there. This may make sense in some applications, but it's kind of looking a little closer to parallel wiring. So maybe this isn't the most flexible option that I want in my system. So maybe I'll use 2 switches. Maybe I'll do this switch tied to the PLC and these 3 IO cards, and then these 2 IO cards will tie to this switch, and I'll run a cable here behind as my backbone connection. You know, the cool part is I could buy a switch here that says, oh, maybe I'll run 100 meg here. Maybe I'll run a gig here. I'll run a higher speed backplane. So if you picture your data, it's like your highway system. Everybody's putting around their back roads, and then you get on the highway and the data goes flying through there much quicker. That allows me to make this pipe and the bandwidth here a lot bigger. If you look at it like a water hose, it's like your main water line coming in versus the T's that come out to the individual faucets. And it just allows more stuff to be pushed through, making the network efficient through sheer bandwidth. And then this also gave us the next cool thing that people were asking for that was pretty hard to deliver with serial. We didn't really talk about it before, and that's redundancy. Having a redundancy connection inside of your network is big. Things go down, things go wrong. Forklift hits a cable, somebody runs something or cuts something they shouldn't. This redundancy mechanism inside of Ethernet allows you to basically run 2 wires in between any one of you can basically run a backup cable in your system, so that, all right, this is my main trunk, here's my backup cable. This cable's more or less turned off until something goes on here, and then it turns itself back on and gives me a secondary path to push the data through. Redundancy. Another feature that was huge inside of these networks that really created the big advantage. And once this hit the market, everybody realized, that's it, serial's over. This is the direction we need to go for everything. And I haven't looked back since. Serial, yeah, sure.
Another quick question here, and it's about Ethernet and how it looks depending on your protocol. So Ethernet IP, Ethernet, Modbus, TCP, they're all Ethernet protocols. Can they all travel on the same line, or does everything have to be independent of each other?
Great. That's actually a great question. I'm glad, because I completely glanced over that. They are all Ethernet is Ethernet. Ethernet was built to be open. Ethernet doesn't care what protocol is running across it. It's just Ethernet. Whether it's Ethernet IP, whether it's Profinet or Modbus, it's still just Ethernet. So the system and the cabling are all identical. So that basically means that on this network, as much as you shouldn't do it, I could hook my computer and do my email on this network at the same time as I'm streaming a YouTube video, watching Netflix, and doing IO communications, because it's all Ethernet. Assuming I have a connection to the internet through this network too. It's all Ethernet.
And just to reiterate, you don't recommend that practice, right?
Yes, yes. Do not ever do it, please. In your home network, like kind of what I'm doing now with my test network, it's all hooked together into one big network because it doesn't really matter. But in a real world application, you would keep all those separate. But in the end, your Ethernet network in your office is the same as your Ethernet network on the plant floor. It's Ethernet. It's just the devices you use. A switch for the industrial plant floors, it has a whole set of different ratings and compatibilities versus the router in the office. That one can't handle the extreme temperature conditions and the robust environments that you're going to do on your plant floor. So there's a difference in the components, but in the end, it's a switch. It's Ethernet. So, but one point that I don't get through, just to kind of double down on top of it, While all three of these, Modbus, Profinet, and Ethernet IP, are Ethernet, and they all run on the Ethernet concept, they all have recommendations. Modbus, there's no real recommendation. They don't care what you use or what functions your switches and what functions your network supports. When it comes to Ethernet IP, they ask that your switches support specific functionalities that they take advantage of, multicast communications, things like that, certain levels of redundancy, port mirroring, quality control, VLANs. These are all terms that switches support and functionalities that they support inside of their network. And these different protocols make what they call recommendations that most of the time you really should follow, but they're not a hard requirement that you have to follow them all. So there is some things there. So you will see like, oh, look, my switch is rated for Ethernet IP. My switch is a Profinet device. Basically, it has settings and all the settings are set for Profinet, or it has settings and they're all set for Ethernet IP. It's pre-configured to function ideally for the network it's supposed to run on. And then, of course, the last one is, as much as we ran away from serial, some people are like, sometimes it was kind of cool just to daisy chain my devices together. So from the IO perspective, we started putting dual Ethernet ports on there, putting a little unmanaged switch so that we could daisy chain the devices together also as an option inside of the network. So we could take advantage of all the flexibility of Ethernet, but maybe have a couple runs of IO daisy chain together. But in the end, I would say all of the above because, well, actually, let me restate that. Not all of the above. In the end, I would say the first and the last is your ideal direction you'd want to go. You have machines. There are always going to be IO points right next to the machine. Of course, just wire them directly to the IO cards that you have for the PLC. And then as you get out of the cabinet and you break into your distances, that's where you're going to start incorporating the distributed IO to collect those signals, use Ethernet to bring that information back. Because in these applications, you're going to end up not just having IO on those Ethernet networks. You're going to have HMIs on those Ethernet networks. You're going to have drives that have direct Ethernet connections in that network. And you're going to be able to network all those components together back to the PLC using that Ethernet network. Because in the end, it's all about getting all this information back to this PLC so this PLC can figure out what to do with it. And then in the end, it sends commands out to all the devices to turn things on or off or to do whatever it's supposed to do. Make your widget. So Ethernet, really the key to the future. There still are some people out there that are still on their serial networks, mainly because I think a lot of it is because it's always worked and I'm not going to change it unless I'm forced to change it. But when it comes to new components and IO devices, everything is going in that direction. It's going to be rare to see devices launched into the market that are going to be, focused on the serial protocols. But over time, the IO module has changed. You saw that picture way back when I showed you the first Interbus boxes. Those boxes were big. I mean, they were half the size of a serial box. That was a huge box for an IO module because the IC chips were, they were larger than my thumb that were on the board for those. So as components change, the designs are changing, and you're seeing that we're kind of moving towards, down in the left-hand corner, larger modules into smaller, and we're reducing the footprint, we're reducing the size, because in the end, we're trying to reduce the size of the cabinet and the size of the footprint of the IO in the cabinet. So either we're going to go with an IP20 option, which you see on the left-hand side. These are all products you would put inside of either a large cabinet or inside of a small cabinet or junction box, we would call it, to collect IO signals and bring them back. Or you take the big leap and you go, you know what? Why do I have a cabinet? Why don't I buy an IO module that is my cabinet? And I can just wire all of my IO signals through standard M12 cable sensor connections and put my network interface right on the box. It's almost going to the level of removing the box into the IP67 realm. All of these are great. All of these have their advantages and disadvantages, but in the end, I look at these as options. It's just a way that you can build your machine to make it better. If you do a quick glance, here's a great picture of two IP67 installations. You can see the IO modules on the right here. All of the sensor connections are done. They're all pre-made M12 connectors. This is great for the applications where they need to be installed on site, and you don't want to have people in there with screwdrivers and stripping wires and putting them into terminals. Oh, I could just use all pre-purchased sensor cables, plug them from the sensor to the I/O device, and then I'll do pre-made power cables here to power the devices. And these are actually Ethernet cables. This is an M12 Ethernet standard that's used for Ethernet devices in the field. So and we're actually here, we're using that daisy chain concept. We're daisy chaining the sensors together. So you can make the leap to this. This is big automotive. This is big conveyor systems, things like that, where you have a small amount of I/O spread out over real long distances. It's a much more cost-effective solution than to do all the junction boxes. And then, of course, you have the I/O in the cabinet. This is still the more popular variation, but in the cabinet, you have the idea of creating I/O stations and creating some modularity between them. The first I/O modules, when I/O was really, the distributed I/O module was invented, it was always a block of I/O. You had a big block. It had 16 inputs and 16 outputs. You'd install it in your machine, and every time you do it, immediately you start wiring it up, and you realize, I need 17 inputs. Now what do? Now you buy another block with 16 in and 16 out. Like, for one, that didn't make sense. So a modularity concept was really key and focused in the I/O market. Phoenix jumped into this early. A lot of our competitors did the same, and we created our modular I/O form factors. This one here, our inline one on the right, is a really cool, and it's been around for almost 20 years that we've been promoting this product. It is a great modular I/O. You just snap together what you need. I need another analog module, snap on another analog module. I need more digital, snap on some more digital, and you wire them into the station. But as you can see, the I/O modules themselves, they can absorb some space. Then space is a premium in the system. And Phoenix is always trying to advance everything that we do and everything that we push. And we're trying to shrink these stations and absorb as little space in the cabinet as possible. And that's really a focus of ours on this left, is this new concept that we called smart elements. If you look and compare these two stations, you would immediately go, oh, look, the station on the right, that has a lot more I/O than the station on the left. To be honest, the station on the left probably has 2 to 3 times more I/O than the station on the right, because the station on the left has really optimized space and availability and wiring to allow us to condense the station as small as possible, because we're moving from just a simple slice I/O to a grid-based I/O, which you can see here on this page, where we're giving you I/O modules, but instead of having it, oh, here's I/O module 1 and then I/O module 2, we're giving you base modules with 4 and 6 open slots, and you just simply snap in the modules you need. So you could do 16 channel input and output modules, or do 32 channels and 15 millimeters of space. It's amazing the space that you can save with this. But this is kind of the trend in I/O, is we're trying to reduce the space. We don't want to take up more space than we need to, but we know we need to supply you your connections for your sensors. We need to give you your LED, your diagnostics, all those functions and features you need. And we're able to achieve that here in this new small I/O portfolio called Smart Elements. This is, this is a huge thing for us in the market. Huge, and mean huge by meaning it is the small and one of the smallest I/O form factors that you're going to find in the market. So it's something you definitely want to take advantage of and definitely push it out. Definitely investigate the possibility of using this, because in the end, you could use these modules to save you and reduce the amount of space even your PLC uses by using smaller chassis. Because this Axioline portfolio and the Axioline Smart Elements are kind of part of a whole family. A family of I/O that gives you the smart elements, or you can do the highly compact smart elements, the standard additional wire I/O that gives you the additional wiring connections. If you're tying this to a Rockwell or Rockwell, Siemens, or Schneider PLC, you can place one of these interfaces on the front, and it can communicate Ethernet up to those stations. But if you're really looking to simplify your system, and you're really looking for a new complete control offering, instead of putting a head station on there, put one of our controllers on there. If you put this head station on the front of this, you're now taking this I/O station and turning it into a PLC. Because a PLC is just it's a brain with I/O. With an interface module, it's just a kind of a dumb interface. So we can turn these this Axioline product portfolio into a full control offering. So if we can replace the PLC, we can replace the IO, and we can replace your network all with an Axioline solution and reduce the space dramatically in the system while giving you the flexibility Ethernet gives you to distribute this throughout the field. So there's a lot going on here, but the idea behind this today is really just to kind of give you a glimpse into where it started and where we're at. And we've moved from modules that were the size of cereal boxes down to modules that are half the size of my iPhone. So we're dramatically reducing space and footprint inside of the offering. But with that, I don't know, Zach, was there any more last minute questions that came in?
First, I want to say thank you very much, Jason, for going through the history of IO, brief history of IO. And some things looking in the future. And there are no further questions, but I'll stall a little bit and go over a few things just in case there's any further questions. We answered them during the presentation.
Okay.
Yeah. One thing I wanted to point out is, we talked a lot about IO and things like that. One thing we didn't get on was new technologies like IO Link or single pair Ethernet or PoE, Power over Ethernet, and we do have presentations on that phoenixcontact.com/us-webinars that handle each of those individual topics. So if you were looking for more information on that, please don't hesitate to jump in or register for any of the upcoming events that are featuring those technologies, or go back and review any that we did previously. The other thing is I did add a link for the Axioline SE into the Q&A, so that's phoenixcontact.com/AXLSE. So you can go in and get more information. You can see it. There's a cool PXR augmented reality experience. You can use your phone or your iPad and take a look at that and basically where it fits in your system. No, I think we're good on questions here, Jason. I don't see anything coming in. I really appreciate the time today. I appreciate everybody staying on with us today. Really good presentation. If you know someone that will find use out of this, or you have someone coming in to your facility and maybe they're just out of school, I think this is a really good presentation to give a good overview of distributed IO and distributed control and really where it came from. And it'll be available on replay as soon as this is over. So, Jason, any final comments?
No, I think I'm glad you pointed out the experience there. And again, with the IO, any questions? My email was there at the beginning of the presentation. Let me know. I'd love talking about IO. So, any questions or more in depth you want to get in on specific things, just give me a call, shoot me an email.
All right, thank you very much, Jason. Thank you to everybody in attendance today. We appreciate you hanging out with us. Go to phoenixcontact.com/us-webinars to sign up for the next available webinars. There's a whole bunch of them sitting out there. So we're looking forward to seeing you next time. And thanks a lot, everyone. Have a good day.